All right. Hello, everybody. Welcome back. Some announcements. So I posted a Blackboard announcement yesterday. I decided to finish the Chapter 9 slides in a recording. That way we have this week to go through Chapter 10 in the beginning of Chapter 11. It's like a 24-minute recording. Just finishes up Chapter 9. You didn't need to watch it for class today, but you'll need it for the final and for the Achieve Homework that's due Monday. So sometime this week, watch that recording. It's on Blackboard Collaborate. And yeah, just finishing. There's just a couple of concepts that we didn't get to in class for Chapter 9. And then today we're starting Chapter 10. So the next Achieve Homework will be due next Monday since we don't have class next week. I have the due time at 11:59 p.m. So you have all day Monday also to work on it. But note that this is the time that the remaining learning curves are due. So I think that's Chapter 7, 8, and then there will be 9 and 10. So 4 more learning curves will be available. Trying to do 4 learning curves and a whole Achieve assignment on the same day will probably be overwhelming, and you might have exams on Tuesday, so just keep that in mind. You distribute your time how you want, but there are a lot that if you're doing the learning curves that will be due on Monday, so just keep that in mind. Chapter 8 learning curve is available now. I'll post Chapter 9 today, and then Chapter 10 I'll post this week as well. But we didn't cover every detail in Chapter 9 or Chapter 8, Chapter 9, and Chapter 10. So I tried to remove some questions, but there might be some that pop up that are not from what we covered in class. So just keep that in mind. If you ever need to send me an email with a question, just do that. I still want to have them available for you to do for extra credit, but I can't remove individual questions. I have to remove whole sections. So there might be something that comes up. So just keep that in mind. That's what that asterisk is for. I have office hours today at 1, Wednesday will be at 2, and then Thursday is at 1:30. We also, of course, have recitation at 8 on Wednesday, and then our final exam for this section is on Wednesday, next Wednesday at 11 a.m. in this class. So we have an hour and 50 minutes. The exam is written to take an hour and 50 minutes, so we'll have that time to finish it. And then 1070 is over. Yeah. Yes. Yeah, it is.
Are you going to post like topics for the final exam?
I hadn't planned to do that. I'll maybe do that this week though. Okay. Thanks. Yeah, no one has asked me to do that yet, so I just wasn't thinking about it. But, yeah. It's all multiple choice, and it's written by American Chemical Society. It's in a packet. You'll have a packet with all the multiple choice questions. You'll have scrap paper to write on, and you'll have a Scantron to write your answers. There's 70. All multiple choice. Was there another question somewhere? Yeah. All right. Okay. So we are starting Chapter 10. This is not the right description for Chapter 10. It's all about covalent bonding. So we talked about ionic bonding and periodic trends in the previous chapter. Today, Chapter 10 is about covalent bonds. So the difference between ionic and covalent bonds is that in covalent bonds, electrons are shared. Both atoms have access to the electrons that are in a bond, so they are shared between 2 atoms. So first section, we're looking at how covalent bonds are formed. So if we have if we're thinking about 2 atoms that are not bonded yet, so here I have 2 hydrogen atoms. Hydrogen has 1 electron, so 1 proton and 1 electron. Again, they're not in a bond yet, but the electrons from one atom are attracted to the protons in another. And then same thing vice versa. Electrons from one, protons from the other are attracted to each other, and that force of attraction causes the atoms to come close to each other. But we still have some repulsive forces. There's electrons in both. Electrons repel each other. They're both negatively charged. There's protons in both. Protons repel each other because they're both positively charged. But these attractive forces stabilize the atoms. And lower energy. So it's a stabilizing interaction, an energy lowering interaction if you have something that's positively charged near something that's negatively charged. So it's a stabilizing effect. If you have two like charges near each other, that's destabilizing. So atoms coming together, there are some stabilizing effects, there's some destabilizing effects. So an actual bond will occur when the attractive forces outweigh the destabilizing forces. This image on the bottom here, I have one hydrogen atom on this side, a proton and an electron. Here we have a molecule. So we have two hydrogen atoms sharing two electrons. So the electron clouds overlap. Both electrons, so the one from one hydrogen, the electron from the other hydrogen, are now part of this entire electron cloud, and both atoms have access to both electrons. So this hydrogen has two electrons in its valence shell. This hydrogen has two electrons in its valence shell. The electrons are shared between the two atoms. So a covalent bond is formed when two nuclei share electrons. And these covalent bonds form when the stabilizing force exceeds the destabilizing forces. So the nuclei to electron attraction is greater than the electron to electron repulsion and the nuclear to nuclear repulsion. Now if we think back to electron configurations, hydrogen has a 1s1 configuration. It has one electron in its 1s shell. For it to have a full valence shell, which is a 1s2 configuration, so one additional electron is needed per hydrogen atom. So if we think about an individual hydrogen on one side of this H2 molecule, this hydrogen now has access to two electrons, so it has a full valence shell. The hydrogen on the other side also has two electrons in its valence shell. So both atoms now have noble gas configuration. So we can represent hydrogen with a dot for one electron. When the two hydrogens come together to form H2, they're sharing two electrons, and we represent that as a bond, so a single line between the two atoms. So in general, atoms, they come together, they share electrons, and they achieve a noble gas configuration. Remember, noble gas configurations are particularly stable because valence shells are full. When shells are full, that is a stabilizing state. So hydrogen atoms, which have a 1s valence shell, gain one electron, which means they create one bond. To obtain the 1s2 configuration, which is the helium electron configuration, we say hydrogen follows the duet rule, where two electrons in its valence shell is the goal for hydrogen. You'll see hydrogen everywhere with one bond. Period 2 elements gain a number of electrons to obtain the 2s2, 2p6 configuration. So we call this the octet rule because there's 6 electrons in the p shell, 2 electrons in the s shell. It's a total of 8 electrons in the valence shell. So something like oxygen, which has a configuration of helium and then 2s2, 2p4. We'll actually talk about this on the next slide, but oxygen will need 2 more electrons to have a 2p6 configuration, a noble gas configuration. So oxygen creates 2 bonds to then have access to 2 more electrons. And again, octet rule because then we have 8 electrons in the valence shell. Now this is true for period 2, elements in the p shell. Elements in the s shell often lose an electron, they are cations. But for n equals 3, so the third period and lower, this is a good starting point to follow the octet rule. But some of these atoms can have more than 8 electrons in their valence shell. So no second row elements can have more than 8. But in the third row and beyond, they can. And that's because they have access to the 3d orbital. So some elements are stable with more than 8 electrons in their valence shell. But what we're working with mostly in our class and mostly in Gen Chem 2 and mostly in organic chemistry are elements in the first and second periods. Okay, so let's go through the slide here. How many bonds is each atom likely to make in a molecule? So we're thinking how many more electrons does each atom need to obtain a noble gas configuration? So let's start with carbon. Carbon has configuration helium, 2s2, 2p2. It has 4 electrons in its valence shell, 2 from 2s, 2 from 2p. To obtain a total of 8 electrons, it needs 4 bonds. Carbon, you'll see also, almost every molecule has 4 bonds. So carbon needs 4 more electrons, so it'll create 4 bonds. Now we can draw a structure for carbon. We're going to draw the Lewis dot structure for this atom. We'll start just doing it for atoms here, and we'll draw Lewis structures for molecules. But to draw a Lewis structure, you'd write the element symbol, and then you can, I'm writing this in the corner, and then we'll actually draw the Lewis structure under the word carbon. But you can think about each element being in a box with 4 sides. Then we distribute electrons as dots around the 4 sides. And we only distribute valence electrons. So carbon has 4 valence electrons. We'd write 1 on each of these 4 sides. So usually we don't draw the box. But if we draw that Lewis dot structure for carbon, we're distributing the 4 valence electrons. So carbon has 4 electrons. It needs 4 more. So I'll make 4 bonds. Now, oxygen electron configuration, helium, 2s2, 2p4. So this is what I wrote on the previous slide. So 6 electrons in its valence shell. To draw this Lewis dot structure, we write the element symbol. We're going to distribute 6 electrons, first 1 per side. So 4 sides, 1 per side, just like carbon, and then we double up. So it has 6 electrons. It needs 2 more to have a full valence shell. So oxygen is stable with 2 bonds. Okay, trifluorine. Let me know if you have questions as you're working on this. Give you all like a minute to try this out. Okay, fluorine electron configuration is helium 2s2 2p5, so it has 7 valence electrons. I added a note here that when we're thinking about bonding, drawing Lewis structures, we're only including valence electrons. Core electrons are not involved in bonding. So fluorine with 7 valence electrons, we write this around element F. So we start 1 on each of the 4 sides, and we start doubling up. Notice we have 1 unpaired electron. This electron will contribute to a bond with another atom that has another electron that can be shared, and then that way fluorine will have access to 1 additional electron. So 7 valence electrons needs 1 more. Fluorine often creates 1 bond. Now note that shared electrons in a covalent bond exist in overlapping orbitals. So if you have, what did we looked at hydrogen, H2. Hydrogen with 1 electron shares its electron with another hydrogen that has 1 electron. So in this bond we have 2 electrons. Both electrons are shared by both atoms. So this hydrogen has a full valence shell because it has access to these 2 electrons. And this hydrogen has a full valence shell because it has access to these 2 electrons. So any electrons in a bond are in overlapping orbitals. They're shared by both elements. A little bit more on these valence electrons. So valence electrons are what we're focused on when we're thinking about covalent bonding. That's because they have sufficient orbital size and energy that they are reactive, but they're not too unstable for bonding. So fluorine has core electrons in the 1s shell, and it has valence electrons in the 2s and 2p. If any electrons had gained energy and went to a higher energy orbital, that would be too unstable for bonding. But these valence electrons in the 2s and 2p are available to form bonding orbitals. Now notice for fluorine, it's missing 1 electron to have a complete 2p shell. And again, that's why it creates 1 bond, to have access to 1 more electron. All right. So what we drew with the electron dot diagrams for atoms, we'll use that to draw molecules. So we'll think about what types of bonds and how many bonds an atom will make. We'll be able to complete structures of molecules. So these are all for covalent bonds, sharing of electrons. So Lewis structures are schematic drawings of molecules. Lewis structures show how atoms are linked together in a molecule, how they are bonded together. It also shows where electrons, or which electrons are shared in a bond and which electrons are what we call lone pairs or non-bonding electrons and are owned by 1 atom. So here's hydrogen chloride. There's a single bond between hydrogen and chlorine. This represents 2 electrons that are shared between hydrogen and Cl. So each line, 2 electrons. Then chlorine has non-bonding or lone pair electrons. Those 2 phrases represent the same or mean the same thing. We're talking about these dots. These are other electrons that are not involved in bonding. So a Lewis structure shows the location of electrons, the connectivity of atoms, but it doesn't show the actual shape of a molecule. We'll talk about shapes later. Some Lewis structures show the shape properly, others don't, so we'll represent shape in a different way. Let's also count electrons in valence shells here. So hydrogen bonds to have a duet, to have 2 electrons in its valence shell. It's sharing these 2 electrons, so we say hydrogen has 2 electrons in its valence shell. Chlorine is in the 3rd period. We're using the octet rule for chlorine. In its valence shell, it has all of these lone pair electrons, so there's 6 electrons here, plus 2 electrons that are shared in the bond. So that's a total of 8 electrons in chlorine's valence shell. So when we're counting valence electrons, we add together lone pairs and electrons in any bond to that atom. So a total of 8 electrons. So both atoms have full valence shells in this molecule. Okay, so to draw Lewis structures, here's hydrogen fluoride. We use the elemental symbols, so the letters, to represent atoms. We only use or include valence electrons, so that's 1 electron for hydrogen and 7 electrons for fluorine. A line represents shared electrons, a pair of shared hydrogen and fluorine, and the dots represent non-bonding electron pairs. Now, if we go back up to the H and F under number 1, and we use the electron dot structure here, well, a hydrogen has 1 electron, so we can add 1 electron for hydrogen. Fluorine, it has 7, so we'll add 7 electrons around fluorine. Hydrogen has 1 unpaired electron. Fluorine has 1 unpaired electron. Those unpaired electrons are shared in a bond so that hydrogen has access to both and fluorine has access to both. Now, something like oxygen, I'm drawing this in the top right corner, O2 gas, 2 oxygen atoms. You can draw the Lewis structures. We have 2 oxygen atoms near each other. We did this earlier. Oxygens have 6 electrons in their valence shell. So we add the Lewis dots. Now I'm going to intentionally leave the electron to the right and the electron on the bottom unpaired, but I have 6 electrons around that first oxygen. And then I'll do the same thing on the other oxygen, leaving the electron to the left and the electron on the bottom unpaired. Okay, so in O2, each oxygen has 6 electrons. Each oxygen needs to be sharing an additional 2 electrons. If we form a single bond between the 2 oxygens, we still don't have enough electrons in each oxygen's valence shell. Each oxygen now has a total of 7 in their individual valence shells. So oxygen in O2 will share 4 electrons. So we have what's called a double bond here. Okay, so some atoms will have multiple bonds with a single other atom. O2, oxygen gas, has a double bond between the 2 oxygens. That's what we have on this next slide here. So HCl, we have a single bond. We have a total of 2 shared electrons. Or we can say for every pair, we have 1 shared pair of electrons. O2, we have a double bond. Each line represents 2 electrons. So that means we have a total of 4 electrons shared, or 2 shared pairs of electrons. Nitrogen has 5 valence electrons. It's in the 5th column. So each nitrogen atom, I drew up right above N2, has 3 unpaired electrons in one set of an electron pair. So N2, there's a total of 6 electrons shared, and this creates a triple bond. Quadruple bonds exist. I don't think we'll see any in our class though. They exist between metals that have expanded octets, access to d and f orbitals. In our class in organic chemistry, we typically see single, double, and triple bonds. Okay, so let's do this learning check. We have two molecules here, hydrazine and hydrogen cyanide. In each structure, identify total number of shared electrons, total number of unshared electrons, and then for each atom in the structure, determine how many electrons are in its valence shell. I'll give you a minute or two to get started, and then we'll work together. All right, if we're looking for number of shared electrons, what are we looking at? The bonds. Yeah, we're looking at the bonds. So bonds represent shared electrons. Each line represents 2 electrons. There are 5 bonds in this structure. So there are 10 electrons total that are being shared between all 6 of these atoms. If we're looking at unshared electrons, what do we look for? The dots, the lone pairs. So here we have a total of 4 dots that represents 4 electrons that are unshared. One pair is owned by one nitrogen, the other pair is owned by the other. So we have a total of 4 unshared electrons. Okay. Now, how many electrons are in each atom's valence shell? We look at hydrogen on the left. How many electrons are in that valence shell? 2. Yes. It has a single bond. It has access to both electrons in that single bond. So each hydrogen has 2 electrons in its valence shell. Now, all of the hydrogens in this structure have 1 bond. So that means all of the hydrogens in the structure have 2 electrons in their valence shell. So they're in the same bonding pattern. They'd have the same access to the same number of electrons. How about this nitrogen? How many electrons here? 5, and I hear 8. Okay, perfect answers. So nitrogen has 2 lone pair electrons, and it has 3 bonds. But remember that bonds represent 2 electrons. So for every bond, it has access to 2 electrons. So total of 6 electrons in the 3 bonds, and then the 2 lone pairs. So nitrogen has 3 bonds, 2 electrons per bond, means a total of 6 that are shared, but nitrogen still has access to all 6. They're all in its valence shell. Plus it has the 2 non-bonding electrons, so it's a total of 8. So nitrogen has a full valence shell. It follows the octet rule. And when you're drawing Lewis structures for molecules, you always want to double check and make sure that each atom has a full valence shell. And then the other nitrogen has the same bonding pattern. The other nitrogen also has 8 electrons in its valence shell. All right, how about hydrogen cyanide? How many shared electrons? 8. Yes, there are 4 bonds total. There's a triple bond, so 6 electrons, and a single bond, which is 2. So 8 electrons are shared, and then how many are unshared? 2. The 2 dots, the 2 electrons on nitrogen represent 2 unshared electrons. Hydrogen has a single bond, so it has 2 electrons in its valence shell. How about carbon? How many electrons in carbon's valence shell? I hear 2 and 8. Or 6. 4. It's 8. Yeah, it's 8. So carbon has a triple bond, which represents 6 electrons. So 6 electrons are shared between carbon and nitrogen. All 6 we say are in carbon's valence shell and in nitrogen's valence shell. Remember, orbitals are overlapping, so both atoms have access to all those electrons. So that's 6, and then plus the single bond to hydrogen, that's a total of 8 electrons. And then nitrogen, 3 bonds again. It's a triple bond, but still 2 electrons per bond, and a lone pair, that's also 8. So in these structures, all atoms have full valence shells, 8 electrons for carbon and nitrogen, 2 electrons for hydrogen. All right. Now, there are multiple ways to reach a correct Lewis structure. This slide and the next 2 slides describe a method that I think is helpful. This is what's in your book as well. So the first thing to do is to sum up the valence electrons for each atom present in the molecule. So you count total number of valence electrons for all atoms. Then select a central atom and arrange the other atoms around it. The central atom is usually the atom that makes the greatest number of bonds. So carbon makes 4 bonds. If you have carbon and oxygen in a molecule, carbon will be the central atom because it creates a greater number of bonds than oxygen. It's also often the first atom written in a formula, unless the first atom is hydrogen. Hydrogen only creates 1 bond, so it cannot be a central atom. So we'll get practice doing that. And then connect the central atom to each of the outer atoms with a single bond. Remember that each single bond represents 2 electrons. After they're all connected with a single bond, then you'll determine how many valence electrons remain. Distribute the remaining electrons to the outer atoms until you used up all that you've calculated in step 1. Then go back to your central atom and see if it has a full octet. And if it doesn't, and you've already distributed all valence electrons, then that means an outer atom is sharing a pair of electrons with the central atom. So you'll have a double bond or a triple bond. And then we verify the final structure. So we make sure that the duet rule is fulfilled for hydrogen. We make sure that elements in the second period have a full octet. In the second period, those atoms can never have more than 8 electrons. If you have an atom in the second period with 9 or 10 or 12 electrons, that's not a valid structure. If you have an element in the third period or lower, that can be a valid structure. You always also want to make sure that in the final structure, the total number of valence electrons, so shared and unshared, equals the number that you calculated in step 1. So we'll do this example here for PCl3. So phosphorus has 5 valence electrons. It's in the 5th column. Chlorine has 7 valence electrons. It's in the 7th column. And so we have 3 chlorines. That means each chlorine brings 7. That's 21 total, plus 5 from phosphorus. We have a total of 26 valence electrons. Okay, so we've calculated number of valence electrons. Now we need to assemble the bonding framework. Phosphorus creates, well, chlorine is in the 7th column. It only creates 1 bond. So chlorine's not going to be a central atom. Phosphorus will be. So we put phosphorus in the center and a single bond to each of the 3 chlorines. You could put a chlorine above phosphorus. You could put them all on the right, all on the left. Doesn't really matter at this point. So far, we have 3 bonds. That means we've used 6 valence electrons. We have another 20 to distribute. Chlorine, so we distribute to our outer atoms first. Chlorine has 1 bond. That means it has access to 2 electrons. It needs 6 more to have a complete valence shell. So we'll add 6 electrons per chlorine. Now each chlorine has a full octet. Now we have a total of 24 electrons in our structure. So we still need 2 more. Well, we need to put 2 more somewhere. If we look back to our central atom, phosphorus does not have a full octet. It's only sharing a total of 6 electrons. So that last pair of electrons go on phosphorus. Okay. Good here. Do another example. Any questions? Okay. We double check, count total valence electrons. Should have 26. Make sure each atom has a full octet, and each atom is sharing a total of 8 electrons. So we're good here. Okay, so let's do CHCl3. We'll do this one. Actually, no. Try this one. If you finish, go to the next slide. I'll give you all, 2 minutes to get started, and then we'll go through them together. So count total number of valence electrons, arrange your atoms.
Yes, it is. That's all natural. Yeah, and then it picks up when you
No, it doesn't. We'll talk about shapes later in this section. So often it's so the electrons we spread out far. So we get them far apart. And put like one over here and one over here. Kind of in the corner, but it's still a valuable.
I did. I like that one. I don't have Yeah, I don't think it's
Okay. For CHCl3, if we count total number of valence electrons, we have 4 from carbon, 1 from hydrogen, 7 from each chlorine. We have 3 chlorines, so that's a total of 21. Add that all together, we have 26 valence electrons. Next step is to arrange our atoms so that the central atom is the atom that creates the greatest number of bonds. Hydrogen creates 1 bond. It can only have 2 electrons in its valence shell. Chlorine already has 7 electrons in its valence shell, so it creates 1 bond. Carbon creates 4 bonds, so carbon will be our central atom. So we've got our central atom. We add 1 bond from the central atom to all 4 other atoms. Now we can check how many valence electrons are already represented. So in bonds, how many electrons are represented in the bonds here? 8. 4 bonds, 2 electrons per bond. So that means that we should have 18 electrons as lone pairs. We need to distribute to outer atoms. Except for hydrogen, only 2 electrons for hydrogen. It already has 2 in the bond. If we look at an individual chlorine, chlorine has currently, the way we've drawn it, 2 electrons. It needs 6 more electrons to have a full octet, so we add those as lone pairs. We've added 18 electrons, so we have a total of 26 electrons, valence electrons in this structure. Each atom has a full valence shell, 8 electrons for carbon from the 4 bonds, 8 electrons for each chlorine, 3 pairs, so 6 dots plus the bond gives each chlorine 8, and then hydrogen, 1 bond, has a duet. Feeling good so far? Okay, let's go to carbon dioxide. So total valence electrons. We have 4 from carbon, and we have 2 oxygens. Each oxygen brings 6 electrons, so 12. So we have a total of 16 electrons in the structure. Anytime you have carbon, that's probably going to be your central atom. Carbon creates 4 bonds, oxygen creates 2, so carbon's in the center. We give each oxygen a single bond to carbon for now. So far we've represented 2 bonds. That's a total of 4 electrons. That means to have a total of 16 electrons, we'd have 12 as lone pairs. So if we distribute the remaining 12 to outer atoms, we can complete oxygen's octet by giving it 6 electrons on either side. That takes care of all 16 electrons now. But we have a problem. Our central atom, carbon, only has 4 electrons currently in its valence shell. So carbon is open shell, less than 8 electrons. Our oxygens are closed shell. Well, to close the shell of carbon, give it a total of 8 electrons. A lone pair from each oxygen will be shared between carbon and oxygen. So instead of that lone pair being dots, it's shared between carbon and oxygen. And we'll do that with both oxygens here. So carbon has 4 bonds, 8 electrons. Oxygen has 2 pairs and 2 bonds, 8 electrons. So both atoms, or all atoms, have a closed valence shell. So instead of 4 electrons in bonds, we have 8 electrons. And instead of 12 electrons in lone pairs, we have 8 electrons in lone pairs. So this is why we double check to make sure atoms have a closed shell. Yeah. We have not talked about that theory yet, so not right now. This is a valid structure. So the question was about geometry. We'll talk about that later. It's a valid Lewis structure. Other questions? This is a very important chemistry skill. You'll do this forever while you're in college in chemistry. Okay, another structure here. Now we have an anion. Now remember, if something's negatively charged, it had gained an electron. So when we calculate total valence electrons, boron is in the 3rd column, so it has 3 valence electrons. We have 4 fluorines. Each fluorine has 7, so that's 28. And we have a -1 charge, so we add 1 additional electron to our total count. So with that minus charge, we add 1 more electron. We have a total of 32 electrons, valence electrons in this structure. All right, fluorine makes 1 bond, so that's not going to be our central atom. Boron will be. We will distribute fluorines with a single bond around boron. We have 8 electrons in bonds here because we have 4 bonds. So our lone pair count should add up to 24 electrons to reach the 32. Boron has 4 bonds. It has 8 electrons in its valence shell, so that's closed shell. We distribute remaining electrons to reach an octet for each fluorine atom. That's 6 electrons per fluorine. We have 4 fluorines, so 24 electrons. So in the structure here, each atom has a full octet. Overall, this structure has a -1 charge. This is the net molecular charge. We'll talk about formal charges later in this chapter and how to calculate them. But we're told it has a -1 charge, so we add that electron. If you had a cation, you subtract an electron. All right, so we've worked with so far pretty simple molecules. As molecules get larger, sometimes they're represented as structural formulas. Right now, chemical formulas, that's what we've seen, this only indicate how many atoms of each element are present. So like propane, we have 3 carbons and 8 hydrogens. But a structural formula indicates how atoms are connected together. So for dimethyl ether, there's 2 carbons, 6 hydrogens, 1 oxygen. This is the chemical formula. But in dimethyl ether, we have a carbon bonded to 3 hydrogens, bonded to an oxygen, bonded to a carbon, bonded to 3 hydrogens. So instead of writing C2H6O, it's represented in its structural formula as CH3, to represent the CH3, O, CH3. So this tells us that this carbon's bonded to 3 hydrogens, bonded to an oxygen, bonded to a carbon, bonded to 3 hydrogens. For propane, that would be CH3, CH2, CH3. Sometimes these are written with line. So again, for propane, we'd have CH3 group line to represent a carbon-to-carbon bond, CH2 line, CH3. So these are helpful to know how atoms are bonded in a larger structure. So again, there's often clues in the formula to help you arrange the atoms in a molecule. In NH2OH, this structural formula here that tells you that the OH tells you there's an OH bond in the molecule. In ethanol, we have CH3, CH2OH that tells you that the first carbon's bonded to 3 hydrogens, bonded to 2. The next one's bonded to 2 hydrogens, and then we have an OH group. When we're writing bonding frameworks, we can talk about inner atoms and outer atoms. Outer atoms are bonded to only one other atom. So outer atoms in this molecule are highlighted in blue. Hydrogens are always outer atoms. Halogens are always outer atoms. They create one bond. And then in this case, you have an oxygen that's bonded to one carbon, so double bonded to one carbon. That's considered an outer atom because it's only bonded to one other atom. This oxygen with 2 single bonds is not an outer atom because it's bonded to 2 others. So hydrogen atoms are always outer atoms in compounds discussed in this text, or in our class. Alrighty, we'll continue on Wednesday. If you didn't pick up your unit exam 2, I have that.
So will like the questions in the exam be like the same like as like the midterm kind of same difficulty?
Yeah, and the multiple choice on the unit exams.
Okay.
Yeah.
Thank you.
You're welcome.